Stephen Hawking's A Brief History of Time. A Brief History of Time. Chapter 8. The Origin and Fate of the Universe. The Origin and Fate of the Universe. Einstein's general theory of relativity on its own predicted that space-time began at the Big Bang singularity and would come to an end either of the Big Crunch singularity if the whole universe collapsed, or at the singularity inside the black hole if a local region such as a star were to collapse. Any matter that fell into the hole would be destroyed at the singularity, and only the gravitational effect of its mass would continue to be felt outside. On the other hand, when quantum effects were taken into account, it seemed that the mass or energy of the matter would eventually be returned to the rest of the universe, and that the black hole, along with any singularity inside, would evaporate away and finally disappear. Could quantum mechanics have an equally dramatic effect on the Big Bang and the Big Crunch singularity? What really happened during the very early or late state of the universe, when gravitational fields are so strong that quantum effect cannot be ignored? Does the universe in fact have a beginning or an end? And if so, what are they like? Throughout the 1970s, I had been mainly studying black hole, but in 1971, my interest in questions about the origin and fate of the universe was reawakened when I attended a conference to cosmology organized by the Jesuits in the Vatican. The Catholic Church had made a bad mistake with Galileo when he tried to lay down the law on a question of science, declaring that the sun went around the earth. Now, centuries later, it had decided to invite the number of experts to advise it on cosmology. At the end of the conference, the participants were granted an audience with a Pope. He told us that it was all right to start the evolution of the universe after a Big Bang, but we should not inquire into a Big Bang itself, because that was the moment of creation and therefore the work of God. I was glad then that he did not know the subject of the talk I had just given at the conference. The possibility that space-time were finite but has no boundary, which means that it has no beginning, no moment of creation. I had no desire to share of the fate of Galileo, with whom I feel a strong sense of identity, partly because of the coincidence of having been born exactly 300 years after his death. In order to explain the idea that I and other people have had about how quantum mechanics may impact the original and fate of the universe, it's necessary first to understand the generally accepted history of the universe according to what's known as the hard Big Bang model. This assumes that the universe is described by a Friedman model, right back to the Big Bang. In such a model, one finds that as the universe expands, any matter of radiation in it gets cooler, and the universe doubles in size, its temperature falls by half. Since the temperature is simply a measure of average energy or speed of the particles, this cooling of the universe would have a major effect on the matter of matter in it. and very high temperature particles would be moving around so fast that they could escape any attraction toward catch each other due to nuclear or electromagnetic focus. But as they cooled off, one would expect particles that attract each other to start to clump together. Moreover, even the type of particles that exist in the universe will depend on the temperature. At high enough temperature, particles have so much energy that whenever they collide, many different particle-antiparticle pairs would be produced. And although some of these particles would annihilate on hitting antiparticles, they would be produced more rapidly than they could annihilate. At lower temperature, however, when colliding particles have less energy, particle-antiparticle pairs would be produced less quickly, and annihilation would become faster than production. And the Big Bang itself, the universe is thought to have had zero size, and so to have been infinitely hot. But as the universe expanded, the temperature of the radiation decreased. 1 second after the Big Bang, it would have fallen to about 10,000 million degrees. This is about 1,000 times the temperature at the center of the sun. But temperature as high as this are reached in H1 explosion. At this time, the universe would have contained mostly photons, electrons, and neutrons, extremely light particles that are affected only by the weak force and gravity. And they are antiparticles together with some protons and neutrons. As the universe continued to expand and the temperature dropped, the rate at which electron-anti-electron pairs were being produced in collision would have fallen below the rate at which they were being destroyed by annihilation. So the most of the electrons and anti-electrons would have annihilated with each other to produce more protons, leaving only a few electrons left over. The electrinos and antineutrinos, however, would not have annihilated each other, because these particles interact with themselves and with other particles only very weakly, so they should still be around today. If we could observe them, it would provide a good test of this picture of a very hot early stage of the universe. Unfortunately, their energies nowadays would be too low for us to observe them directly. However, if neutrinos are not massless but have a small mass of their own, as suggested by some recent experiment, we might be able to detect them indirectly. They could be a form of dark matter, like I mentioned earlier, with sufficient gravitational attraction to stop the expansion of the universe and cause it to collapse again. About 100 seconds about the Big Bang, the temperature would have fallen to 1,000 billion degrees. The temperature inside the hottest stars. At this temperature, protons and neutrons would no longer have sufficient energy to escape attraction of the strong nuclear force, and would have started to combine together to produce the nuclei of atoms of deuterium, heavy hydrogen, which contain one proton and one neutron. The deuterium nuclei would then have combined with more protons and neutrons to make helium nuclei, which contain two protons and two neutrons, and also small amount of a couple of heavier element, lithium and beryllium. one can calculate that in the hot Big Bang and model, about a quarter of the proton and neutron would have been converted into helium nuclei, along with a small amount of heavy hydrogen and other elements. The remaining neutrons would have decayed into protons, which are nuclei of ordinary hydrogen atoms. His picture of a hot early stage of universe was first put forward by the scientist George Gamow in a famous paper written in 1948 with a student of his, Alphe. Gamow had quite a sense of humor. He persuaded the nuclear scientist Hans Besser to add his name to the paper to make the list of authors Alpha, Beta, Gamma, like the first three letters of the Greek alphabet, Alpha, Beta, Gamma, particularly appropriate for a paper on the beginning of the universe. In this paper, they made a remarkable prediction that radiation in the form of the proton from the very hot early stage of the universe should still be around today, but with its temperature reduced to only a few degrees above absolute zero, minus 273 degrees Celsius. It was this radiation that Penzias and Wilson found in 1965. At the time was Alpha, Beta, and Gamma wrote their paper. Not much was known about the nuclear reaction of protons and neutrons. Predictions made for the proportions of various elements in the early universe were therefore rather inaccurate, but these calculations have been repeated to the right of the better knowledge and now agree very well with what we observe. It's moreover very difficult to explain in any other way why there should be so much helium in the universe. You are therefore fairly confident that we have the right picture, at least back to about 1 second after the Big Bang.